So in this lecture, we're going to talk about Lewis structure, which is a covalent bonding. We talked about ionic bonding previously. So Lewis model provides simple model for covalent bonding. Lewis structures depict the neighboring atoms as sharing some or all of their valence electrons. So we make use of valence electrons in bonding in order to attain octet structure or duet if it is hydrogen. The shared electrons will count towards each atom's octet. Each atom's octet. The shared pair is called the covalent bond. So this is what I mean. For example, if you want to show the bond between chlorine atom, so when we draw the Lewis dot structure for chlorine, two atoms of chlorine, it's gonna have, each of them, we have 7 valence electrons, and we write the valence electrons this way: 1, 2, 3, 4, 5, 6, and 7. The second chlorine atom has 1, 2, 3, 4, 5, 6, and 7. So in this Lewis structure, because it is covalent bond, it involves electron sharing. So each of them will donate an electron each, and they're going to form a bond this way. So this single bond has 2 electrons. So we now say the shared electrons we count towards each atoms. So what it means is that I have 2 electrons here because chlorine wants to be an octet. So I have 1, 2, 3, 4, 5, 6, 7, 8. So each of these we count towards this chlorine atom this way. So I have something like this. So we have 8 electrons for chlorine. This chlorine atom is octet. Then the second atom of chlorine is going to take this also. So it has 1, 2, 3, 4, 5, 6, 7, 8. So this is what we have in chlorine atom. All right. So for oxygen, we have 2 oxygen atoms like this, and each of them has 6 valence electrons, which we are going to distribute this way: 1, 2, 3, 4, 5, 6. And this also has 6 valence electrons. Right. Okay. So we're going to make the first bond. Right. And we count. Each of them has 1, 2, 1, 2, 3, 4, 5, 6, 7. Same thing for this atom. However, we said they are looking to become octet, meaning they are looking to have 8 electrons. So since this is 7, the goal is that each atom we have an octet structure. So we're going to move electrons to make multiple bonds. So we can move this electron here, this one, we can move it here. We can move this one here, and we make another bond. So this one has gone, this one has gone. So we make another bond. So when we count, this is 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen has all these 8. So it's complete. And these two 4 electrons here, 1, 2, 3, 4, 5, 6, also is shared by the second oxygen. So everybody is okay right now. So we are not going to make any more bond. So we have that. Let's go to nitrogen. Nitrogen has 5 valence electrons. 1, 2, 3, 4, and 5. So here we have 1, 2, 3, 4, and 5. So we make the first bond from here. This one has 1, 2, 3, 4, 5, 6. So we still need more. So we can move these electrons here. And we can move this here and make another bond. So we have 4, 5, 6, 7. Right, still not complete. So we can move this one from here. And we can move this one from here and make another bond. Since we have moved them, they're going to go away. Right. So we now have 6 here. 1, 2, 3, 4, 5, 6. This 6 electron belongs to both of them. So the first nitrogen gets this, which makes it 8 octet, and this second nitrogen also gets it. Right. So we have that. So that is how the electrons are shared, so that each of them can attain octet structure. So the next thing we now do here is that whenever we have a bond like this, we call this one single bond. Whenever we have two this way, we call this double bond. And this one is gonna be called triple bond. All right. So in single bond, we call it the single bond contains 2 electrons, or we can say 1 pair. For double bond, it has 4 electrons, or you can say 2 pairs. And triple bond has 6 electrons, or we can say 3 pairs. Okay. In this Lewis structure, we have what is called bonding electrons and non-bonding electrons. So the electrons that are actually taking part in the bonding, in case of oxygen right now, these electrons here, they are actually participating in the bonding. So we call them bonding electrons. And those that are not taking part in the bonding, just like these, all these ones here, they are not part of the bonding, right? We call them non-bonding electrons. Non-bonding electrons. So we should be able to look at bond and distinguish non-bonding and bonding electrons. For example, if you are asked how many bonding electrons and non-bonding electrons do we have in nitrogen molecule? You take a look at nitrogen molecule. We have six bonding electrons. All the electrons here, they are bonding electrons. So 6 bonding electrons, and a total of 4 non-bonding electrons. These and these are non-bonding, so they have total of 4. So that is how we identify all these bonds. And so for these bonds that we have, single, double bond, and triple bond, the weakest of this bond is the single bond. Single bond is the weakest. And the strongest of all this bond is the triple bond. Right. So we want to look at writing Lewis structures for molecules. Writing Lewis structures for molecules. For molecules, that especially heteroatomic molecules that we have different atoms and they are more than 2, we have rules that we use to write the structures for this molecule. For example, let's say we want to draw the Lewis structure for SO2 molecule. Right. So we have 3 atoms here, 2 of oxygen and 1 of sulfur. We cannot just write it the way we have done these ones, because we only have these are homoatomic, which is same element but 2 atoms, just 2 atoms. But when it comes to this, we cannot just use that. We have rules that we have to follow, and I will show us how we apply rules. The first rule is we need to calculate the number of total valence electron. Calculate the total valence electron. So how do we calculate the total valence electrons? So for SO2, for example, so we know that we have 1 of sulfur and 2 atoms of oxygen. So we go to our periodic table, which we can use. We know that sulfur has 6 valence electrons. Remember, we have 1 of sulfur and 2 of oxygen, right? So sulfur has 6 valence electrons, and oxygen also has 6 valence electrons. So we have 6 plus 12, and the total valence electron for this SO2 is 18 electrons. Let's say you are asked to find the total valence electron for HNO3. Right. So we know that we have 1 of hydrogen plus 1 of nitrogen, 1 atom, plus 3 atoms of oxygen. Right. So we now find the valence electron of hydrogen is 1. The valence electron of nitrogen is 5. And the valence electron for oxygen is 6. So we have 1 plus 5 plus 18, and that gives us 24. We can also find total valence electrons for polyatomic ions, also polyatomic ions. In this case, for polyatomic ions, we have to remember something. For every negative, you add. for every positive, you're going to subtract. So this is what I mean. This is a polyatomic ion, NO3, which is nitrate. If you want to find the total valence electron for nitrate ion, so we say we have 1 of nitrogen plus 3 atoms of oxygen. And remember, this is a negative. What do? We add. So it's going to be 1 into 5 plus 3 into 6 plus 1. So we have 5 plus 18 plus 1, and that gives us 24. Let's say we want to find for ammonium ion. So we have 1 of nitrogen plus 4 of hydrogen. So, and this is positive, right? So for every positive we do what? We subtract. And it becomes 1 into 5. Nitrogen has 5 valence electrons. Oxygen has 1. Then we subtract our 1. So we have 5 plus 4 minus 1. That gives us 8. One more example. We have CO, carbonate ion. So this is going to be carbon, 1 of carbon plus 3 of oxygen. Plus, this is 2 negative, right? What do? We're going to add 2. So we have 1 into 4 plus 3 into 6 and plus 2. So this is going to be 4 plus 18 plus 2. And that should give us 24 again. All right. So that is how we find total valence electron for any of the molecules or polyatomic ions that we have. So for every negative for polyatomic ions, it can be cation or anion. So for every negative, you add for every positive we had. So the rule number 2 is we need to find the best arrangement of the atoms. Arrangement of all atoms. Because this arrangement is very critical. If we do not arrange very well, there is no way we can make all the atoms to achieve octet structure. So we have certain rules we need to observe whenever we're trying to arrange these atoms. So what we do is that we place the least electronegative element at the center. Place the least electronegative I'm gonna be using En atom or element at the center. And if you have hydrogen, you place hydrogen at the terminal. All right. So in case there is hydrogen, we place hydrogen at the terminal because hydrogen is always looking forward to become a duet, not an octet. So even if hydrogen is the least electronegative stuff that we have, we do not place it at the center, we place it at the terminal. So let's take, for example, our SO2 Right. So between sulfur and oxygen, if you look at the periodic table, sulfur is least electronegative between oxygen and sulfur. So we're gonna, because we have three atoms here, we have two of oxygen and sulfur. So we can have this arrangement. We can also have this arrangement. We can also have, OSO. So only one is acceptable. So the rule of arranging the atoms helps us to choose which one is going to be. So we already said that um, sulfur is the least electronegative, so it's going to be the central atom, and oxygen is going to dance around it that way. All right, so that is the best arrangement for SO2. If you have NO3, like our nitrate, the same thing. Between nitrogen and oxygen, the least electronegative is nitrogen. So we're going to make nitrogen to be at the central atom, and oxygen, we have three, is going to dance around it that way. Right. For example, if you have HNO3, so because we already know we have hydrogen, so hydrogen is always going to be at the terminal. We are not going to consider if hydrogen is the least or whatever in this molecule. So what we need to do is to just use nitrogen and oxygen, and we find the least electronegative, which is going to be nitrogen. And you're going to have your nitrogen as the central atom. We have three atoms of oxygen, right? So hydrogen is going to be placed at the terminal, right? This way. So it's either you place your hydrogen here, or you can decide to place your hydrogen here at the top. It's up to you. You can place it here, or you can decide to place it here. It doesn't matter. It just has to be at the terminal. We have only one hydrogen, so it's just only one. So that is what we mean by the arrangement of the element, of the atoms. So this is this and that. Okay. So the third rule is to distribute all the valence electrons. Distribute the valence electrons. The valence electrons that we calculated, that we first observed, so this is number 3. The valence electron that we calculated at step 1, we're going to distribute all these electrons. And how do we do that? First, you distribute around the atoms surrounding the central atom. Distribute around these atoms. Distribute first on atoms surrounding the central atom. Then place the leftover electrons. Place leftover electrons on the central atom. Okay, so this is what I mean for our SO2 molecule that we're using. We already said that this has 18 valence electrons. We already said that the arrangement is going to be this. This is the least electronegative, is going to be central atom, and that. So we want to distribute these 18 electrons on this. So we say that we need to place on the atoms surrounding the central atom. These atoms surrounding the central atom are just these 2 oxygen atoms. So we now ask ourselves, how many electrons do we need? We have, this is the first atom of oxygen, this is the second one. For the first atom of oxygen, how many electrons do we need to add to this to make oxygen an octet? If you take a look at this single line, remember, it means this is, we already have 2 electrons with oxygen. Oxygen is looking forward to have an octet structure, meaning it's looking forward to have 8 electrons. So oxygen already has 2 here. Remember, these 2 electrons belong to oxygen and it belongs to sulfur. So when we say it belongs to oxygen here, it means that oxygen needs 6 more electrons to become an octet. So we now say 1, 2, 3, 4, 5, 6. So these are the 6 electrons. So we subtract these electrons from 18 because we are making use of this valence electron, which is 18. So we have 12 more left. So we now go to this second oxygen, oxygen number 2. Oxygen number 2 already also has 2 electrons, which is this, and it also needs 6 more to be stable octets. Right. So in this oxygen here, oxygen number 2 is octet. It's smiling because it's stable, right? So we subtract this 6 again from the remaining, so we have 6 more left. Now, the next thing we do is that we now go, remember the rule says we should distribute on the surrounding central atoms surrounding the central atoms, which we have done. And it says place the leftover electron on the central atom. Our central atom is sulfur. So we now say on sulfur, remember these 2 electrons belong to sulfur also, right? This is 2 and this is 2. So sulfur already has 4. So we subtract that 4 from sulfur. Minus 4, it gives us 2. So this is the leftover electron. So what we do is we place this leftover electron on the sulfur. So it's going to be this. So we have minus 2, everything is 0. So we have finished distributing all the 18 electrons that we have. So we have finished distributing all the 18 electrons around this. So the next thing is we now check. So I said the next thing we do is we now check if all the atoms are happy, that is, if all electrons have obtained their octets, all the atoms have obtained their octet number or structure, we leave them as it is, and if not, we can now move electrons. We move electrons to make multiple bonds. So this is what I mean. We already have our sulfur SO2 to be this. We need to check, is everybody having octet structure? If you take a look at this oxygen number 1, we see that oxygen number 1 is fine. It has 1, 2, 3, 4, 5, 6, 7, and 8, right? So it's good. If you look at oxygen number 2, is 1, 2, 3, 4, 5, 6, 7, and 8. It's also good. And let's look at sulfur. Sulfur has 1, 2, 3, 4, 5, 6. Sulfur is not smiling here, right? Because sulfur needs 8 electrons. So in that case, what we do is we can move, we move electrons to make multiple bonds. So we can move electrons from any of the oxygens surrounding the sulfur, right? Because sulfur, this molecule can form resonance, right? So if I decide to move from my oxygen number 1, I'm going to move these electrons here. Remember that whenever we have a single bond, single bond represents 2 electrons, right? So we still remember that. So these 2 electrons will form a single bond here, right? So because we have moved it, it's going to disappear, right? So, and remember this bond, these 2 electrons is both for sulfur and for oxygen. So in that case, we can count 1, 2, 3, 4, 5, 6, 7, 8. So sulfur is happy. And oxygen is also happy because these 4 electrons here belongs to oxygen again. And we have 4 plus 1, 4, 5, 6, 7, and 8. So everybody is happy right now. So the Lewis structure for our SO2 is going to be this. We have 2 of these electrons here and this one, S, and it has 2 electrons here. And we have the 6 here. So this is our Lewis structure. I just drew it appropriately here. So for SO2 molecule. So let's take another example for ammonia. This is ammonia. So the first rule says we should calculate the valence electron, total valence electron. We have 1 of nitrogen plus 3 of hydrogen. So, and this is going to be 5 plus 3 into 1, which is going to be 8. So we have total of 8 valence electrons. Like in this arrangement, the next thing is we find the arrangement for this. So this arrangement, this is hydrogen. Hydrogen is always placed at the terminal, so we don't need to check for electronegativity. So we just know that nitrogen will be the central atom, and your hydrogen is going to dance around it, right? We have 3. So we put them together. So we want to distribute all these 8 electrons, right? So what we have is total valence electrons to be 8. So if you look at hydrogen here, this is my hydrogen number 1, 2, and 3. Right. How many electrons do we need to make hydrogen happy? None, because hydrogen, remember, is looking forward to be a duet. It's not looking forward to be an octet. This is 1 electron here. This is another one, which is 2. So hydrogen is okay. So we need nothing. The same thing goes for our hydrogen number 2, is already having 2 electrons. Remember, these 2 electrons belong to this hydrogen as well as nitrogen. So the same thing applies to our hydrogen number 3. So it doesn't need any. So we have 8 minus 0 for hydrogen number 1, which is T8. For hydrogen number 2, minus 0, which is T8. For hydrogen number 3, it is 0, which is T8. So now we go to our nitrogen, which is our central atom. So our central atom, remember, these 2 electrons also belong to nitrogen. Belongs to nitrogen, right? So we now count 1, 2, 3, 4, 5, and 6. So nitrogen already has 6 electrons around it. So we subtract that. So it's now remaining 2. So what do we do to these 2? Right, this is a leftover these are leftover electron. Leftover electron. So we place the leftover electrons on the central atom this way. So we have -2, which is going to make everything to be 0. Right. So because we have 0, it means that we have finished distributing all our 8 electrons here. So we now check. The last thing is we check, is everybody okay? Like this is okay, this is okay. And nitrogen is already having 1, 2, 3, 4, 5, 6, 7, 8. So everybody is okay. So the Lewis structure for our NH3 is going to be NH, H, H. We place the leftover electrons here. So that is going to be for our NH3. So we want to do for a polyatomic ion, which is NO3. Remember, we already did the valence electrons before. Let me go there so that we don't. So we say our valence electron for NO3 is 24, right? So we just bring that 24 down. It's gonna be 24 valence electron. And we also said the arrangement is going to be, because nitrogen is the least electronegative, so we're going to have oxygen dancing around it. As usual, oxygen here needs 6 more electrons to be happy, that is to become octet. So we subtract that 6 from here, it becomes 18. Then this also needs 6 more, right? To be happy, we subtract that, it's gonna be 12. This also needs the oxygen atom 1, 2, 3. This one also needs 6 more to be happy. So -6. So we have 6. We now go to the central atom. The central atom already has 1, 2, 3, 4, 5, and 6. So we subtract that. So 0. So that we have spent all the 24 valence electrons that we have. So the next thing is we need to check, is everybody happy? Now, the oxygen number 1 is happy because it has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen number 2 is also happy. Oxygen number 3 is happy. However, let's check our nitrogen. Nitrogen has 6. Nitrogen is not happy, right? So nitrogen is not happy. So what do? We can move electrons from any of the oxygen atoms around the nitrogen. So I decide to move from my oxygen number 3. So I want to move these 2 electrons here from my oxygen. So remember again, these 2 electrons means a single bond. We place it here. I'm going to place it here. So, and since I've moved it, this is going to disappear. So we now check again, is everybody happy? So we can see that these 2 electrons here is 4. So this is going to be 4, 5, 6, 7, 8. So right now, nitrogen is happy. This oxygen is still happy too, because we have 4, 5, 6, 7, 8. So this is how our, remember, we have to place it in this. So let's remember that we had this negative was what made it to be 24. You place it there. So the new, the Lewis structure for our NO3 will be this. We have 4 here, and this oxygen is 6. We have our oxygen here, so it's 6. And do not forget to place it this way. So these are a few examples. I hope we can use this to solve as many examples that we have. So the next thing I want to show us is the exceptions to the octet rule. Exceptions to the octet rule. What are the exceptions to the octet rule? Number one exception is odd number electron species. Odd number electron species. For example, NO. If you look at NO, the valence electron is 5 plus 6, which is 11. This is an odd number electron species. This is odd number. So whenever you have any of these, they are not gonna be they are gonna be exception to octet rule. Because if you draw the Lewis structure for this guy here, NO is gonna be this, right? We have 5, 1. This one has 5 valence electrons. So this is gonna be 11. So when you distribute this, it's gonna just give you we have 5 valence electron, and this has 6 valence electrons. 1, 2, 3, 4, 5, 6. All right, when you make this way, you're gonna have that. If you move these electrons to make multiple bonds, this one and this one, right? This one goes away, right? You're gonna see that this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is happy, but you're gonna see that this nitrogen is not happy. So if you move more electrons to make multiple bonds, it will never make both of them to achieve octet structure. So these are odd number electrons. So we say they have unpaired electrons. So they have unpaired electrons. They have unpaired electrons. So this is the unpaired electrons in nitrogen here, and this form of free radical. Free radical, and which makes them very reactive. Very reactive. That is one exception, right? The another exception to octet rule are electrons with incomplete octet. Incomplete octets, like we have in boron and Al. For example, if you have BF3, if you use all the rules, BF3 is going to be like this. If you use the rules to draw the BF3, it's going to be this way. This is what you're going to have with BF3. BF3 is going to give us a Lewis structure that looks like this. So when you distribute all the valence electrons and do all the stuff, it's going to give you this. And you can see that even though all this fluorine, they are happy and happy and happy. So this one is not going to give you boron, it's going to give you just 6. right? 1, 2, 3, 4, 5, 6. So those are exceptions. Then we also have the last exception that we have is expanded octets. Expanded octets. So for expanded octet, we say elements with empty d orbitals. Elements with empty d orbitals, right, can have more than 8 electrons. Can have more than 8 electrons. So remember that in d orbitals, d orbitals can have maximum of 10, and the f can have like 14. Remember that. So we have that. For example, in our PCl5, PCl5 is going to be 1, 2, 3, 4, and 5. Our Cl is going to be that, and that. So this is going to be this, and Cl is going to be that, 6 here, 6 here. By the time you use all the roots, you're going to give so it's going to give you that. So when you do that, you're going to see that phosphorus P here has already 10 electrons. So these are expanded octets. These are exceptions to octet rule that we have discussed. So I hope we can use this to solve problems on how to how to draw Lewis structures for molecules. Thank you.